and start recording. Okay.
All right, so yeah, I think we're good to start then. Can you pass over screen sharing?
Yeah, oh, right. Co-host. So yeah, okay. So now that we're recording, I'm just going to start off with a brief overview since we are recording this and most people will be watching this on YouTube. I think most people just like watching the recordings, but yeah, for those who are watching on YouTube, we are IEEE Ottawa student branch. And for those who are new, I know most people just find us not directly from like our pages, but they find us through Discords. So for those who are new, we are a student branch of IEEE, which is a global professional association with more than 400,000 members for electronic engineering and electrical engineering and its associate disciplines. And in addition to us being a student branch, we're also a sub-association of ESS, the Engineering Student Society, and we represent electrical engineering, computer engineering, and software engineering students. So we host a lot of events for students. We host a lot of technical workshops and networking events, social and academic events, and we run like these review sessions every semester for students. And we actually have AGM coming up, which is their annual general meeting. So if you want to join IEEE and go for the by-elections, you can do so. You can follow us at IEEE uOttawa on Instagram to learn more about it. And so yeah, I'll pass it on to Juan for our ELG2137 review session.
Hey, so I'm Juan. I'm the IEEE uOttawa branch's Midtown director, and I'll be giving you a brief cookies and cram regarding the ELG2137 Circuit Theory 2 course material. So just we'll check. You can all see my screen. I'm gonna wait till I get like a thumbs up or something. Okay, great. So I'm going to be going over the general course material first, and then questions at the end. If you guys have any specific questions, like examples or something that you'd like me to cover, I can go over that at the end as well. So first we have the operating amplifier. We actually have a couple of those laying around here in the office. I'm not exactly sure which cabinet they're in, but they're here somewhere. And so you would likely find them in a package like such, where you have your inverting and non-inverting inputs and your output and your real inputs. So with regards to what the course covers with them, you could use them into specific circuits to amplify your voltage output. So you can have an inverting amplifier, which changes the polarity of the voltage. So you can see that if you give it a positive voltage in, it actually gives you a negative voltage out, and vice versa. You can have an alternative inverting amplifier that actually sums the differences. You can have a non-inverting amplifier, which as the name suggests, gives you a positive output for positive input and vice versa. And again, an alternative version of such. You can have the voltage follower, very, very important circuit. It isolates your source or your signal from your output. This can be really important if you're dealing with high current loads or if you're dealing with sensitive equipment. And you can see that the output is 1-to-1 with the input, but there's no closed connection. And you have the differential amplifier, which gives you a amplification ratio R2 over R1 with your out and input resistors, related to also the difference in voltage between your non-inverting and your inverting inputs. So you can also solve systems of equations with these, and I'll be covering those at the end during the examples. Next topic to go over is first order circuits. So RC resistor capacitor or RL resistor inductor circuits. So for these circuits, you have to remember some specific little nuances. Specifically that the voltage of a capacitor and the current of an inductor are continuous. That means that they can't jolt instantaneously, meaning that the current at any given point will be roughly the same in a very short time span after, for both the current of an inductor or the voltage of a capacitor. So if you're dealing with a DC circuit and you're trying to solve for them, you can solve with your what's called the forcing function. You basically try and solve the function of time of what you're looking for with respect to it as a first order differential equation. So this tau value that you will deal with here is called the time constant. It's specific to your circuit. This isn't the simplified form of a Thevenin circuit. So you can see you only have one voltage or one current supply from Norton and one resistor, as well as your capacitor or your inductor. And in those cases, you have a time constant of RC for an RC circuit or L over R. Those correspond to the charging and discharging curves. I'm not going to get too into that, but that's basically where they come from. And so to solve for these, you have a steady state and an initial state that you want to solve with. I'll be going over an example first order review, although I'm pretty sure that's covered in circuit theory 1. So for second order RCL circuits or RC circuits, depending on how your prof wants to call them, you get a little bit more complicated of an answer. So usually questions dealing with these ask for the complete response of a component or of an element in the circuit. So to go about this, you're either given the initial conditions, or you must find them. If you have to find them, you do something similar to what you do in a first order circuit. Remember that at steady state, capacitors and inductors behave almost like an open or short circuit, respectively. This is due to the fact that at full charge, a capacitor will simply not allow any current to go through. And at full charge, an inductor will behave effectively as a full conductor. So if we're trying to find the steps to find the complete response is first we find the differential equation through one of two methods. And then we solve the differential equation by finding both its natural response, which is the general solution to the homogeneous portion, and the forced response, which is the particular solution to the inhomogeneous portion. So that's sort of the brief overview. To go through that, first you find the differential equation. You can either do so through the direct method, in which you have an x1 and x2 value corresponding to either voltages or currents for either your capacitor or inductor, respectively. And you want to get two functions, one of which is x1 is equal to some sort of constant and the derivative of x2. Another one is x2 equals some sort of constant, a derivative of x1. You solve both for whichever one you need. So you either plug in x2 into your first equation or x1 into your second equation to find a single differential equation. You can also do the operator method, in which you replace d over dt with s. Math students get really angry when we do that, but that's not really a problem. We can just treat d over dt as a variable and solve it as a linear system. So now when we're solving these, you're going to get a general circuit function represented as the forcing equation, or the forcing function is equal to some second order differential equation with constants. So we can actually turn this into a forced input and have this very specific form of an equation. So for the natural response, you want to set that the forcing function is 0. So a good way to remember that is if you have to force the circuit, you're getting the forced response. You're not getting the natural response of the circuit. Yeah, I can send these after. So for the natural response, you set the forcing function to 0, and then you find the characteristic equation of your ODE. So that will depend on which function you have, but if you have one in this form, you can just transfer it to the operator form, and then find your S value. So what I mean by find the S value, you're just going to solve this as if it were a quadratic formula. And then based on what your determinant is, so b squared minus 4ac, you're going to see what sort of roots you have, and that will give you whether or not you have an over-dampened, critically dampened, or under-dampened circuit. So over-dampened is when you have unequal roots or unequal solutions to S in the operator function, but they're both real. And thus the natural response will be a sum of them with two constants that you're looking for, A1, A2, S1, S2. You know S1 and S2, you don't yet know A1 and A2, but you can find those. Critically dampened is when you have S1 and S2 being the same. So that'll be when your determinant is 0 and you have a single real root. And underdampened is when your two solutions are complex conjugates. So they are a real value plus or minus a imaginary value. In which case, this is the sort of form of your natural response. Your forced response, on the other hand, you want to keep the f of t value, your forcing function, and then reference this nice little table. I don't know, I can check it near the end if it's on your formula sheet for the final. I have an old one as well. If it's not on your formula sheet, you just have to remember these 5 transformations. They're not terribly bad. Some of them are pretty intuitive. Like if you just have a constant, then you just have a constant response of a different value. If you have a linear value, then you have a linear function. These are all general responses, by the way. So constant goes to constant, linear goes to linear, quadratic or second order goes to quadratic form. A sine has a sine and a cosine component, and then exponent stays exponent. So these are pretty easy to remember if you're not given. But anyways, you're going to find what the forced portion of the response is. And your complete response is simply the sum of both of those. So it's the sum of the natural response and the forced response. Once you do that, you're going to have 2 unknown values in your solution. But you're also going to have 2 functions and your initial conditions. Your initial conditions are usually going to be in the form of voltage at t equals 0 equals, or d of voltage at t equals 0 equals something. It's usually given at the top of the question, or something you can find from the base circuit. And using that, you can find all of your unknowns and then solve for the complete response. So now we're moving on to AC analysis. This portion of the course becomes really useful later on in your courses following this one, especially the phasor analysis. So like this is a really important part of the course to like learn from like a solid foundation. So any function for a sinusoidal signal or sinusoidal function, you can represent in its periodic form. So you have its peak or its magnitude. You have the cosine of an angular frequency in a phase, which can be given in degrees or radians. An angular frequency is simply the radian constant, so 2 pi multiplied by frequency, or divided by the period, where the period is 1 over the frequency. And you can actually convert this to a phasor value, a phasor being a vector in the time axis, if that's easier to understand. Basically, you have a way to like think about this is if you have a sinusoidal function moving through time at a certain function or at a certain rate, certain frequency, you kind of ignore the frequency when talking about phasors. You just assume everything has the same frequency if you're working in phasors. And then you just talk about the phase shift. So you talk about voltage having a certain magnitude heading in a certain direction in time, which is the phase shift. So the conversion is actually pretty simple. You can just pull the values straight out of your function. So if you have V of t is equal to peak voltage, cosine of the angular frequency times time plus the phase phasor is simply the peak with an angle shift of the phase shift. Do note that there's another form, or actually there's two other forms of representing phasors. And I can write those in here as well. If you'll let me edit. Let's combine. There's edit. So those other forms are, you would have V equals yeah. So V equals Vn times e to the j omega, or sorry, not j omega, to the j, I guess in this case it would be phi. So that. So this is one other format. It's simply this angular shift represented in exponent notation. Or you can represent it in Cartesian form or rectangular form, which is simply Vm cosine phi plus j sine phi. So I'll be making that a little larger just so it's a little easier to read later. There we go. Great. We also now have to deal with the complex impedance of the components, of your elementary components. So you have your resistor, your capacitor, and your inductor. And when we're talking in the AC, all of them have a form that you can think of them in, which is the impedance form, which simply just means how much do they impede the flow of AC current or of AC electron flow. The impedance of a capacitor, you can represent as 1 over j omega c, where c is the capacitance, or the division of the voltage phasor by the current phasor, both of them for the capacitor, in which case the current is leading. And by leading, we mean that if you look at it on a curve, on a graph, and you look at the sinusoidal function of the voltage and the sinusoidal function of the current is ahead. So at the same point on both curves, the current is further ahead. You can also say inversely that the voltage is lagging or the voltage is behind by a certain amount. For inductors, it's the other way around. Inductors have an impedance of j omega L, where L is the inductance. You find it through the same method. And you find that the shift between them is that the current is lagging. This is an L. I don't know why it's a C here, but it's an L, or at least supposed to be. My handwriting is not the neatest. Apologize about that. And the impedance of a resistor in AC is strictly the its own ohmic resistance. So impedance is measured in ohms. And I don't think it's in these notes, but I'll quickly just touch on it. There's also another, I guess, inversely related value to impedance, which is called conductance. If impedance is how much a medium does not want to allow electron flow or how much it wants to impede electron flow, conductance is how much it wants to conduct electron flow or how much it wants to allow electron flow. So now we get into a review of AC power. So sinusoidal means periodic, means you have a function of which you can actually take an average value. The average value being the division of time multiplied by the integral of the area, the integral of the function or the area under all of this curve. So if you were to add up all of that area, what average value do you end up with? We also use a different value, which is used pretty often, the root mean squared value, of which I have color coded here. The root of the mean, so the average, squared. So we have this average value here that we were talking about earlier. We would simply take the root of that average and then square it internally. So you would square the value, take its average, square root it. This is only really usable for sinusoidal waves, this little comparison here, but you can sometimes say it's the peak voltage over the square root of 2. That's what this simplifies for if you have a full sinusoidal wave. And by a fully sinusoidal wave, I mean it has its center point at 0. We also have what's called instantaneous power, which is simply the power at one point in an element. So if you have a certain voltage and you have a certain current, you have a certain power or a certain amount of energy going through. And you can also get the average of that through the same function shown above. But you can also have what's seen as complex power, or not full-on complex power, but the power phasor form, which is simply half of the real component of the complex conjugate of the voltage multiplied by the complex conjugate of the current. So complex conjugate is a specific thing in phasors. It's sort of shown here. If you have a, thank you, Ethan. If you have a phasor such that x is equal to the magnitude of x with a shift, the complex conjugate is the same magnitude with the negative shift. That makes a little bit more sense later on when we talk about the value of how the rectangular components are. So just move up to where I had those. Yeah, so you can see for the cosine value, if you make phi negative, one of these inverts and the other one doesn't. Thus you keep what's called a complex conjugate. So let me see if using the annotate tool and see if this looks good. Okay, so if you have a graph like this line is terrible. Let's do a better one. Okay, if you have this and you have the vector, as I mentioned earlier, of this is I with a magnitude of IM and a phase shift of theta. In this case, we use phi, but theta can also be used for angles. If we used the negative shift of that, so if it had the same magnitude, but the negative angle, you can see that the cosine portion or the real portion, since it does not have the j associated with it, you can see that the real portion would actually still be the same. But you would have a negative imaginary portion. And what we call those values, where we have a equal real value and opposite imaginaries, is the conjugate. So that's where the term complex conjugate comes from. So anyways, going back to that, but you can also grab this value from this approximation here. And here you have your phase shift. I remember cosine 0 is 1. So if there's no phase shift, it's just half of the values multiplied. So next up we get to complex power, which if this is the real portion of it, this is the full complex portion of it. So you can represent it as half of the phasor multiplication of voltage and the complex conjugate of current, or just the multiplication of the RMS voltage and complex conjugate of RMS current. That's because, as we mentioned earlier, the RMS is just the phasor over root 2 for fully sinusoidal functions. So root 2 times, sorry, 1 over root 2 times 1 over root 2 is just 1 over 2. And thus you can get rid of this if you just use the RMS values. It is also the sum of the instantaneous real power plus the, or not the instantaneous real power, of the real power plus the value of the imaginary power. So you can get the length of this value or the absolute magnitude of it by simply taking the square root of the magnitudes of it, or getting the real and the imaginary portion, getting the length of the phasor. And based on what value you have for your imaginary power draw, you can actually tell whether your circuit is resistive. So it has a 0 imaginary value. So it only has real power draw, and by extension, only has real resistance values. So no J values anywhere. If Q is greater than 0, it's inductive and lagging, as we had mentioned earlier. And if it's less than 0, or if it's negative, it's capacitive. So remember, the impedance for an inductor is usually a larger value or positive. And this is all scaling with the magnitude of the inductance, by the way. Or as the capacitance gets larger, the value of the inductance, of the impedance of the capacitor gets lower. And thus the negative value for the imaginary portion of this. So we can also get the full impedance of the circuit as simply the division of the voltage and the current, or of the RMS voltage and the RMS current, or the magnitudes of the RMSs with the phase shift of both. And you get your nice little Ohm's law, voltage equals resistance times current, except in this case, it's impedance times current in this scenario where you have a phasor sinusoidal circuit. As well, you can represent your complex power through this as simply the multiplication of the impedance and the RMS current times the complex conjugate of the RMS current. Since you're multiplying them, you can actually just skip to having the value of the RMS squared over the phasor of the impedance. So that's just a nice little shortcut if you have those values available. So now we can talk about power factor. It's a pretty simple concept. And it's strictly just how much real power do you have over your, how much of the power is real, or how much of the impedance is resistance. So in this scenario, if it's lagging, it's an inductor, and if it's leading, it's a capacitor. Note that that matches the same thing for the values of Q, of the imaginary resistance, or sorry, imaginary impedance. And if the value is 1, so if they're 1-to-1, or all of your, or the value of your complex power is the same as the magnitude of your real power, they are the same. Thus, there is no shift, and it's simply a resistor. So now let's get away from the sinusoids for a bit, and let's talk about coupled inductors. They can also be referred to in other contexts as transformers, or they can be used into transformers. But for now, let's just talk about them as coupled inductors. So I was kidding when I said we were leaving phasor. We're actually right back to it. But basically, the idea of this is if you put two inductors and you couple them together, in reality, an inductor, you can actually represent it as a coil of wire around the magnetic rod. And in this scenario, you have two coils of wire, coiled around the same magnetic rod. So you have two inductors that are not touching, or at least they're not conductive to each other, but they have the same magnetic core. And due to this, you can actually relate the inductance of both with how much voltage gets transferred between them and the currents that get caused by them. Do remember that it's important to note where the ends of each of them are. And by that, I mean what direction they're coiled in. So usually it's indicated by dots. And for the extent of this course, that's what you can represent them as. And you can get power values represented through the coupled inductors. So now let's talk about transformers. Transformers are inductors with different rates of coupling. And by that, I mean different coils wrapped around the same rod, same magnetic core. So suppose we have a voltage on the input side. Let's call V1 our input side for these. And suppose we have a 1 to 3 coil ratio. So your input has 1 coil, your output has 3 coils. That means that if we have an input of, say, 1 volt phasor, so 1 volt with no shift, your output is going to be 1/3 times your output is going to multiply by that. So in this case, to solve for this, you would go the other way around, and you would have your output is equal to 3 times your input over 1, or your output would be 3 times higher voltage or 3 volts. Current is the other way around. So for current, you would actually have a negative value, first of all, since you're going, as you can see here, you're always going in the opposite direction. You would have a negative value, and you would multiply instead by your coil ratio, and then you would multiply by your coil count, and then divide by the other side of the transformer's coil count. Note that these signs get swapped. So the voltage becomes negative and the current becomes equal if you have opposite-sided paired inductors. We can treat a transfer function as basically something that you give an input and it gives you an output of a function. So if a function is a mapping of a value, a transfer function is a mapping of a function. Bit of a weird idea, but like bear with me, it makes a lot of sense after. So simply put, it is the value of your input over the value of your output. You can treat it as voltage gain, so output over input. You can treat it as current gain, output over input. You can treat it as transfer impedance, so voltage output over current input, or transfer admittance, which is current output over voltage input. So they do have a gain, which is what we call this value. The division of them, it's actually the inverse. And they have a shift, which is simply the subtraction of the shift of the output and the input. So the transfer function usually has a numerator and a denominator, and based off the amount of roots each of them have, you have zeros or poles to them. This becomes really important when we get into Bode plots. In this scenario, suppose you had x squared plus x plus 1 on top, and you had x minus 2 in your denominator. You would have 2 roots in your numerator, so you'd have 2 zeros, and you would have 1 pole or 1 root in your denominator. That's just the general idea of it. So for a Bode plot, as we mentioned earlier, you can turn a phasor into this representation, which is simply its magnitude with a phase shift, or its exponent representation. And because of this, we can actually grab the logarithmic gain, which simply is the gain transferred onto decibels. And using that, we can actually make a plot of how the transfer function affects the original function. So we rewrite the transfer function as some constant, and then 1 plus the values here, which are ordered. So all of these frequencies, so we have frequency of 0, 1, frequency of 0, 2, frequency of pole 1, frequency of pole 2, etc., are values that you get from your original transfer function. And these regular omega values, or these original like radio frequency values, are simply whatever the frequency of the input you give it are. So there's a couple different frequencies that we're dealing with here, and that makes a little bit more sense once we get into filters, which is the next part of this. So just bear with me for a second. So next up, we find omega is between 0 and omega Z1. So in this case, we have 0, 1, 0, 2, pole 1, pole 2 as our rate. So we're gonna say it's constant before that. It has a value of the first one. So omega over Z1 between Z1 and Z2. So after the one before Z2. And we're going to keep going, and we're going to keep multiplying these values in or dividing by them as we reach the point we're at, until we get to this final point where we even out again at what you can see is a constant. So for these values, you would grab the log of them, the base log 10 of their absolute value, multiply by 20, and that is your logarithmic gain. So you can see here that we have the different logarithmic gains. Note that I am using the plus and the minus form of the multiplication, since you can do that with logarithms, and it makes them a little bit easier. And what you end up with is you end up with these values with a slope that you can then apply to them within certain ranges. So from 0 to omega Z1, so omega 0 and 1, we have a slope of 0 at a magnitude of 20 log K, which is here. And then from Z1 to Z2, or from 0, 1 to 0, 2, we have a slope of 20 decibels per decade. Decibels per decade is a weird unit. So we're just gonna hand wave that one for now, but that's the unit you go with. The next one would be 40 log omega, so 40 decibels per decade. You can see that we're going up by that amount every time we increase the power of omega, and that's simply because we can move it down. So for each power, we actually double the decibel rate. But then as we lower the power again, so you can see we went constant, linear, quadratic. We went back down to linear, and the slope went back down to 20 decibels per decade. And as we go back down to constant, or for the final portion, a constant value of 20 log K pole 1 pole 2 minus 20 log 102, that actually gives us a slope of 0, but a constant value of this. This is a bode plot, and you can use those later on for filters to better visualize what the transfer function will do to your function based on what frequency you get. So then we move on to resonant circuits. These have what's called a network function and a resonant frequency, which is a frequency at which they have different behaviors. These network functions can have a maximum magnitude based on the resistor that they're given, and a quality factor, or how much they can transfer across for the values that we're looking for, based off of all three R, L, and C components, and a bandwidth of component based on simply the RL or the RC filter or RC components, based on whether they are a series RLC or a parallel RLC. More of a table that you sort of memorize rather than like try and drill in the basic understanding. It's a lot of simple functions. I'm pretty sure a fair bit of them are given. So you should be fine with that. Just thought I'd cover it. And now we get into filters. So here's where the transfer functions make a bit more sense. So recall that I mentioned earlier that a transfer function is a mapping of a function to another function. So let's use the function f of x equals 2x. So that maps any value of x, so let's say 1, to another map value of x, 2 times 1 equals 2. The transfer function, in this case, what it does is that at certain values, so as a piecewise function, it maps your entire function to a separate group of values. So a low-pass function or a low-pass filter, what it does is that if your frequency is below what's called the cutoff filter or the cutoff frequency, it lets you have the full frequency. In an ideal scenario, you actually would have some cutoff in a real scenario, but let's talk ideal for now. You have all of the original magnitude of your function before that. And then once you reach that cutoff frequency, so when your frequency is larger than the cutoff frequency, your value is 0. So this means that your new function actually has a different mapping. Your new function, rather than being a full, let's say linear, now is linear up to a certain point and then cuts off. A high pass is the other way around. If your value is too low, it doesn't have anything. If it's high enough or higher than the cutoff frequency, you have the full value. Next up, we have what's called a band pass filter, meaning that only things within cutoff frequency 1 and cutoff frequency 2 are allowed to go through the filter. Anything else gets filtered out. Or we have a band stop filter or a notch filter, in which we are cutting out a specific section of the wave. Let me quickly check if I have a graph of them, and if not, I can draw one out quickly. Okay, so I'll draw one out quickly. So get the annotations, and I'll try and do this. What if I use this? That did not do it. We will not be using that. We're using this step. So here's a couple of graphs. So for a low pass, this is frequency and this is magnitude. If you have a cutoff frequency, everything up to that cutoff frequency is a 0 until you reach that frequency, and then you get your regular value. So I'm going to use yellow for what the original function would have been. And then after that, you get your regular function. I'm going to use yellow as well here to represent all of them. Just so it's a bit easier. And I'll set my cutoffs while I'm at it. Let's see. This one is a 2 values. Let's see, 1 and omega, let's see, 2. And here we have the same as well. So what does this mean for us? So for a high pass, sorry, this one is opposite. I was not reading it well. It's my bad. Why? Oh, because I'm on the drawing mode. There we go. So let's say we have your function. This is allowing everything up to that point to pass. So this is fine. This is fine. This is fine. Cuts off. No signal. A high pass would say you have nothing up until that value. And then from that value onwards, you have 1 times the value. So this does not amplify. This allows you to have the base value. Here we have a band pass, which means we have nothing if it's less than. We have the full 1 if it's within those 2 values. And then we have a nothing if it's greater than. And then for a notch pass, we would have something up until that value, then nothing within that notch. That's why it's called a notch pass. Here it's a band pass because only a band of it can pass. Here it's a notch pass because everything except a notch of it can pass. Okay, so I'll clear that now and then keep going. So you can make filters. You can make filters as first order functions or second order functions. And you use you can use your elementary components. So you can use passive filters with resistors and capacitors or resistors and inductors, or you can use active filters using operational amplifiers. You can get a function for them as well, such that you have your low and high pass, where you have your how much gain you can get with them, and your frequency is defined by the max over √2 with them. And for second order, they have either full-on RLC components, or they have active components like operational amplifiers. They have transfer functions of second order. And the reason we would want to use a higher order filter, I'll show that now using a Bode plot. So let's get some nice little graphs again. So here I'll just show two low pass filters. Actually, here, let's go. So I'm going to do a first pass on the left, sorry, a first order on the left and a second order on the right. So ordered, if you have an ordered, quote unquote, filter, it means that it's acting as a real filter, which means that it's not ideal in the sense of full cutoff. So let's talk about that now. If you had a first order, you would have a value leading up to it and then a flat. So note that because of this slope, which we talked about earlier, 20 decibels per decade, you don't actually get 0 here. This is not 0. Suppose that instead we had a high pass filter that had second order. So it had one portion like this and one portion like this. So the slope here is 40 and the slope here is 20. Note that for some portions, this is already much lower than this value is. So while they both start here and while they never actually hit 0 on their own, except when frequency is 0, they actually do have the ability to get you closer to the ideal scenario. And if you used the filters that are below, which are just a systems of transfer functions at higher orders, you could get something that approximates this roughly, and then flat. And this is about as close as you're ever going to get to this in real conditions. And that's why you would use a higher order filter. So yeah, you can see here you have different order filters, and that just simply changes what scale your filter has to truly eliminate the values it's looking to filter out. So now we're going to talk about Laplace transforms. Laplace transforms are very much so a just reference the table sort of thing. You either memorize the table or you reference the table. Pretty sure for this exam it's given. You grab individual linear components in a function, them one-to-one to what the Laplace transform for them would be, with a step function applied to them. So remember that the inverse Laplace transform of a Laplace transform function gives you the function back. So you can use a fractional form of your Laplace transform, use partial fractions to get a sum of them, and then convert them all to their time equivalent after through the above table. So basically this is used whenever you don't want to really deal with the heavier, not quite the heavier math, but the, I guess, more complicated functions. Like it can definitely be easier to work with a constant 1 or with a linear 1 over s. than it can be to work with the impulse function or with the step function. Or to work with all values of S rather than working with mixed exponents, linears, exponentials, and sinusoidal values of T. So Laplace transforms are really just a convenience thing. Like we use them to make life easier. We also have complex analysis, which we can get the initial values with. So this is more so referencing we had talked about earlier, which is that capacitors and in time at the value of 0 in complex, just have 1 over CS, where S is a representation of J omega. And for inductors, you just have LS, where S is a representation of J omega. These are just slightly more general ways of talking about the transfer functions and impedance. Do note that there's such a thing as the impulse function and the step function, which will affect what your transfer functions are. This becomes important later on in your electrical engineering program, but right now they're not very likely to show up. And that's pretty much the gist of it. Like that's the theory for the course. Here's the formula sheet I had. I forget if it was from my year or it was when I got it the year before. But you're given some Laplace transforms right away, specifically the properties of Laplace transforms. You're given what the transforms are. You're given the transform functions for some filters. Also the silent keys as well. You're actually given what the characteristic equations and the differential equations are for parallel and series RLC circuits, which is quite nice. And you are given the table of forced and assumed responses. Or again, when I took it, that's what was given. As well as the time domain and frequency domain representation of circuit elements. Please remember S is just J omega. It's just so that we don't have to write J omega. And you do get some of the conversions, specifically the phasor conversions and the transformer relations. And yeah, so that's pretty much it that you get for the final. Was your exam when you took this on multiple choice? Because this is no, if I remember correctly, the exam had a couple long answer questions or like fully like developed questions. They're not too bad though. Honestly, this course is inherently just a math course with a lot of electrical engineering fundamentals built in. If you can get a really solid grasp on the math and remember the processes, it's no harder than ODE in that sense. So in terms of questions, I can either go over like just random questions on the topics, or if you guys have any specific topics that you'd like me to go over questions on, that'll be a little bit easier.
Yeah, we can probably
way that we should go about it.
You can probably share it on the site server.
Sorry?
The sites, wait, do you guys hear me?
Might be just me, but it's like you're cutting out for me.